till now we have studied how a particle moves and what we described as kinematics, a description of motion. Now, today and in the next series of 3 or 4 lectures, we will look at what are called the laws of motion, and the question which we will try to answer is, what governs the motion of a body? And to understand this, the first thing which we do is we need to introduce the concept of force. Now, if we try to define force, I think we will be going in round and round circles. Maybe we will use some words to define force, but if we look at it, what we can say is that force is a quantitative measure of mechanical interaction of material bodies. That means, if we have two bodies and they interact with each other, then they interact with each other through a quantity called force. And one thing we realize, which we observe in nature, is this force could ensue between bodies, either when the bodies are in contact, or in some cases force could also be there if the body, even if the bodies are not at contact, or they are not touching, then force could be conveyed through a distance. And we will look at examples of all these things, but just to illustrate, if I touch the table and if I touch it, I feel a force on my hand, and similarly a force is being applied on the table by my hand. And if I take an object and if I drop it, then the object is moving and the earth is applying a force on this object, even though there is no contact between the earth and this object. So, therefore, in both the situations, whether there is a contact or there is no contact, if there are two bodies which are interacting with each other, there could be a force between these two bodies. And throughout our this series, when we talk about force and laws of motion, we will see how do we quantify this sort of interaction between bodies. And we will see that these interactions are quantified through some laws, and those laws are what we will study during the course of these series of lectures. Let us try to characterize some properties of force. So, first thing what we realize is that force is a quantity which has a magnitude and this is obvious from the fact that if I press the table lightly or if I press the table very hard, I feel a different sensation on my hand. So, therefore, in one case the force is less, in the other case the force is more. So, it has a magnitude, but not only does it have a magnitude, it also it has a magnitude and it also has a sense of direction. So, and as we have seen that quantities which have a magnitude as well as a direction, these quantities are referred to as vector, and Also what we had described earlier when we talked about these, every quantity which has a magnitude and direction need not be a vector, but vectors have some other properties. For example, vectors follow parallelogram law of addition or the triangle law of addition, and also they transform according to a particular relation. And what we find is that force does follow these laws. So, force is a vector quantity. That means it will, if two forces have to be added, there will be two forces with different directions, and the addition will follow the parallelogram law of addition, or you could use the triangle law of addition, which is equivalent. So, what we do is we represent force by an arrow. The length of the arrow is proportional to the magnitude of force, and the direction of the arrow gives the direction of the force. And this particular statement which I have made, that it's the length of the arrow is proportional to the magnitude of the force, this becomes more pertinent when we are talking of two different forces. They will have their own magnitudes, and then the lengths will represent the ratio of these two forces. So, the ratio of the lengths will represent this ratio. So, that is how we represent a force. Now, one thing which we observe, and this is very a subtle thing which we realize is, and this comes from observation, there is no proof for this, and what we say is that the force which we see, this is not dependent on the frame of reference in which force is being measured. Now, can we say the same thing for all scalar or vector quantities? So, what I am saying is, now frame of reference is, as we have seen, a same quantity could be measured in a frame which is fixed on the surface of the earth, or something which is moving. Let us say a car is moving, we measure the quantity from the moving car. And the point which we are making here is, if we look at forces, forces will not depend on whether you are observing the force from a stationary frame of reference or a frame which is moving with constant velocity or constant acceleration or variable velocity, variable acceleration, whatever it is. Force does not depend on the frame of reference. Is there any quantity which depends on the frame of reference? Very obviously, we have seen that when we look at the position vector, we fix a coordinate axis and we mark the position vector, and it obviously depends on the frame of reference. And not only position vector, we have also seen velocity and acceleration which we measure, they are frame dependent quantities. So, let us just say, as opposed to position vector or velocity or acceleration which depend on reference frame in which they are being measured. And once again, this observation which we have for force, this is valid in the realm of classical mechanics, where we say that the speeds with which we are talking are much less than the speed of light. So, all the arguments which we are going to talk about in this chapter, and at least throughout this course in the mechanics part, are what we call as classical mechanics, which is where we are not considering the effects. So, the speeds are much less than the speed of light. So, now let us try to see, if we have a body in contact with a second body. That means I have a body A and a body B, and these two are touching. So, this may be body A and this may be body B, and there is a contact between these two bodies. So, if we have a contact, the contact between A and B can give rise to a force, and example of such forces, when we see examples of such contact forces, let us illustrate this, are forces what we call as reaction forces, and among them are included, within these reaction forces we have things like a friction force. Whenever a body is sliding on a surface, then we see that there seems to be a force which tends to prevent the relative motion between the two surfaces. And when we have this force between two bodies or two solid bodies in contact, we call it as the friction force. In addition to this, if suppose I have a body, let us say an aeroplane which is travelling in air, so then in this case air is in contact with the aeroplane, and air will put what we call as a viscous force on the aeroplane. So, therefore, these forces such as reaction forces, friction forces, viscous forces are examples of forces which arise because there is a contact between two material bodies. Another example of a contact force could be, suppose if we have a dam here, that is a wall, and there is water on one side. Such a thing is what we call a dam, where we have a wall which is preventing the water to go. Now, here when water touches the surface of the dam, water will exert a force. We call this as the hydrostatic force. So, this is another example of force which comes because of contact. But in addition to this, what we have seen is there are some other forces which do not require any contact between the two bodies. But once again we realize there have to be two bodies for these forces to occur. Example of this, as I had already illustrated, the first example is the force due to gravity, and we looked at it in the sense of when a body is being pulled toward the surface of earth, but Newton also generalized it to universal law of gravitation. If there are any two masses, they exert a force on each other even when they are close to each other, and here this force of gravity, as we will see, I am just speaking in a very qualitative way right now. This depends on, is proportional to 1 over r square, where r is the separation between the two bodies. In fact, it is not only the magnitude, the direction is also specified by the law of gravity, and we will look at this later. But in addition to gravitational forces, there are forces due to between two charges. If we have two charges, a charge q1 and a charge q2, then there is a force between these two charges which we call as the electrostatic force. And then we also have, in addition to this, we have electromagnetic force, which is experienced by a charge which is moving in a magnetic field. Now, once again, for these electrostatic and electromagnetic forces, there is no contact. These forces occur through a distance. Now, let us try to see what is the qualitative effect of a force. And the simplest way in which we can explain is that a force tends to push or pull a body along its line of action. So, that is the, I think, the simplest way in which we can describe a force. Now, once we will later on we will also see that along its line of action a force tends to push or pull, but if we look at the effect of force from a point other than its line of action, then we will also see it tends to rotate a body about a point which is not on its line of action, but this discussion we will postpone right now, will come in when we talk of rotational motion and motion of rigid bodies. So, that is in a qualitative way what we see is, so but what happens when we say a force tends to push or pull a body, what does it actually tend to do to the body? So, by pushing or pulling, what the force tries to do is it tries to alter the state of motion of a body. This is the effect, if I look at it in terms of kinematics, what the force does to a body. For example, let us look at this pen. This is lying on my hand, it is at a state of rest. I apply a force, and as I increase the force, I see that the pen starts to move. So, that means the effect of this force is that it tends to alter the state of motion. If the body is at rest, then it will tend to start the motion of a body, or vice versa, if a body is moving, then we can bring it to a state of rest by applying a force. And so, now this is just a qualitative way of trying to see what a force does. The quantification of this, what we have said qualitatively, the quantification of these statements, this is what we will study by laws of motion. Laws of motion will quantify how the effect of force in terms of the state of motion of a body. But before we do this, let us explain, let us define some more basic concepts. So, the first thing which we define is a concept of a particle, and what we will say is a particle is an entity of finite mass, but infinitesimal size. That means, at a time particle occupies only one point in space. So, if we are talking in terms of coordinates, what we can say is the particle is at x, y, z, the spatial location at time t. So, this is how we idealize a particle. Now, this is an idealization. I use the word idealization because everything which we know has a finite size. So, when we want to consider the motion of a body such that its physical size is not important, then we idealize it as a particle. And for example, when we talk of motion of a ball or a freely falling ball, as we have seen in projectiles, then the ball is assumed to be a particle. And at least for the purpose of the next few lectures, we will assume all the bodies on which we are applying the laws of motion are particles. And this is as opposed to, for example, let us say there is a rod of length L, and we want to study the motion of this rod. suppose I am applying a force at this point, and if I apply a force at this point, then it is possible, or maybe at some other point there is another force being applied, then different points in the rod may have different velocities. And in that case, we cannot idealize the rod as a particle, and as we will see later, we will talk about it as a rigid body. We can maybe at this point just define the concept of a rigid body, which will come in much later, but I want to at least get you to start feeling the notion of a rigid body. A rigid body is a set of particles such that the distance between any two particles is always the same. Now, this will not mean that the particles have all the particles on the body have to move with the same velocity, as we will show, but at least just keep this definition in mind, and currently we will just focus on particles. Now, when we say we have a particle of mass m, and the main thing is, when we talk of a particle, the mass of a particle is finite, it is not infinitesimal, and we observe the motion of the particle from some frame f. What we find is the particle has a velocity v, it has an acceleration a, and maybe we will start, it also has a position vector r. Now, what we also find is the mass of the particle this is always constant, and this again comes when we are talking in terms of our classical mechanics. Mass of our individual particles will always assume to be constants, and if we talk of two particles, the sum of their masses will be equal to, if that particles A and B, then ma plus mb will be equal to, if both of them are combined together, the mass of the new body will be equal to ma plus mb. So, masses add linearly when particles are combined. So, now we define, we have seen mass of a particle which is constant, and this mass does not depend on the frame of reference. We have a quantity velocity of the particle which we have already seen, and using these two we define a new quantity, and which is critical to our laws of motion, and we define a quantity called momentum. We use a symbol p with a vector. In your textbooks you may find a bold faced p which will represent this quantity momentum, and momentum is defined as, so we will say p is defined as the product of mass and velocity. So, that means we are multiplying a scalar with a vector. So, the net resultant quantity is also a vector. So, p is a vector quantity and it is a product of mass and velocity. Now, let us start looking at the laws of motion. This definition of momentum we have seen, we will be using it when we come to our laws of motion. Now, what we observe is that if a body is at rest, then a force is required to make it moving. And similarly, if a body is moving, a force is required to bring it to rest. But next question which we ask is, it is very clear a body at rest, to make it start moving, force has to be applied. If a body is moving, if you want to stop it, a force has to be applied to it. But then the question comes, if a body is in uniform motion, we have explained this before, but let us try to understand this, because we will be using this term uniform motion again and again. Uniform motion means a body moving in a straight line or along a straight line, we can use whatever, with constant speed. So, if a body is moving all along a line and its speed, let us say v is equal to constant, then we say this is in uniform motion. And you will easily realize this also implies that the velocity of the body is constant. So, uniform motion is the same as saying the velocity is constant, or we will say it is moving in a straight line with constant speed. All these three things are synonymous. Now, the next basic question we ask is a force required to maintain the state of uniform motion? That means, I have got a body which is moving in uniform motion or with constant velocity or with constant speed on a straight line. Do we need a force to be applied on this body so that this state of motion can be maintained? And for a long time, Aristotle, the Greek philosopher who was in 322 BC, he had his ideas that to keep a body moving at uniform velocity, a force is needed. And these ideas are what people followed for a long time, but it turns out this was wrong. So, let me, while Aristotle said this, that a force is needed, let us put a cross on this to show that this was a wrong notion. And basically it was not Aristotle's fault. What he understood was, if you see this practical thing, that if there is something which is moving and if a body is there, you give it a push and leave it, then it comes to a rest. So, therefore, to maintain its motion of uniform velocity, a force needs to be applied. But what Aristotle did not consider was that because this body is in touch with the body, second body, in this case my hand below, the hand applies a force of friction, and that is what is stopping the body, and this was not considered by Aristotle. So, there is a friction force, which is when there are two solids in contact, or a viscous force which tries to oppose the relative motion, but this was not considered. Then it was Galileo who was from Italy from 1564 to 1642, who first observed this, and he refuted Aristotle's idea. And what he said was that for a body to maintain its state of uniform motion, no external force is required. And how Galileo got this? Let us try to see. There were some very nice insights because of which Galileo could make these observations. let us look at a motion of if there are two inclined planes, and what we see is if a body, let us say there is a ball which rolls down the incline. We take this example because when a ball rolls down the incline, the friction force is very small. So, when it rolls down the incline, because of the gravity, the acceleration as it moves down, this is positive. The speed of the ball keeps on increasing, but when it moves up the incline, then the acceleration is negative. So, if the same ball is starting with some speed here and it moves up the incline, then there is a negative acceleration. So, now if we try to reduce the angle slowly and we come to a state where there is a level surface. So, there what will happen, from if there is positive acceleration here, negative acceleration here, then on case of a level surface, it will be very intuitive to expect that the acceleration in this case will be 0. That means, if the ball is moving with acceleration on a plane surface, then its acceleration will be 0. So, it will just keep on moving without any force being applied to it. So, this was the idealization how he reached this, and then he also did a thought experiment. You take a ball and you put two inclines together, as we have done there. Of course, we are looking at the motion separately. If this ball comes here and let us say this angle is theta, this angle is alpha, it travels a distance d1 down the first incline, and after coming here it starts to go up, and the distance it travels up the incline is d2. So, what is observed is, if theta is equal to alpha, then d1 is nearly equal to d2. So, then what, and also what you observe is, if angle alpha is greater than theta, then the distance d2 is less than d1. That means, if this is more steep, it goes up a lesser distance. So, we first take alpha which is greater than theta, we find this distance is less, then we reduce alpha, we bring it equal to alpha, we find this distance is equal. So, now when we reduce it more, so we take alpha less than theta, then we find d2 is greater than d1, and then suppose if alpha is made 0, then what one would, if we keep on sort of looking at in the same way, then what we find is that we would expect this distance d2 to go to infinity, which would mean that if this angle alpha is 0, then once the ball comes here, it keeps on moving on this surface, which would say that no external force is required. So, what Galileo said was that if a body is in a state of, so what Galileo's observation was, if a body is at a state of rest or in uniform motion, then both these states are equivalent and no force is required to maintain these states. So, that means whether the body is at rest or is at uniform velocity, the body tends to maintain its own state, and this property of the body to maintain its state of rest or uniform motion, this property we refer to, we call it a special name, this is called inertia. So, basically what we can say is a body does not change its state of rest or uniform motion unless an external force is applied on it. And this essentially is also referred to as Newton's first law of motion. Well, historically it happens, in fact Newton was a British scientist, and Newton was born in 1642, the year in which Galileo died. But what Newton did was he compiled, he studied motion of bodies, and he gave what we term as 3 laws of motion. And the first law of motion is essentially what Galileo had already said. But since Newton compiled all the laws, so therefore we refer to this as the first law of motion, or Newton's first law of motion, which is valid for a particle. And what Newton's first law, essentially we have stated that, and in Newton's terminology, the first law says that each body continues to be in a state of rest or uniform motion unless compelled by an external force to act otherwise. Now, here what we have, that means what we are assuming is, if a body is in a state of uniform motion, there is no external force acting on it. And we should probably qualify this statement slightly, because when we say there is no external force, it gives a sense of feeling that no force is acting on a body. But what we also realize is that it is possible that 2 forces are acting on a body, and the net resultant of these 2 forces is 0, which is equivalent to saying that there is no net force acting on a body. So, therefore, we should, instead of saying it that no force acts, maybe the correct way to word it will be that there is no net force acting on a body, or some of the external force acting on a body, if they are 0, then the body will tend to be in its state of rest or uniform motion. So, the instead of individual forces being 0, the net force, different forces may act on a body, but if the resultant is 0, then also this law will be valid. So, and other thing which we realize is that when the body is in rest or uniform motion, is there some common kinematical quantity which defines these 2 states, a body at rest or a body in uniform motion? And the common kinematic quantity which we can see is acceleration, which in both these cases, whether the body is at rest or the body is in uniform motion, has got to be 0. So, therefore, what we can deduce is, if the net external force on a body is equal to 0, then its acceleration is equal to 0. And this may be another way, or a quantitative way of looking at the first law of motion. So, now we could have two types of situations. There are two types of situations we could handle. The first one is, if we know that sum of all external forces acting on a body is equal to 0, then we can say its acceleration is 0. But normally in real life, finding whether sum of all external forces is 0 or not may not be so obvious. But from a measurement viewpoint, more often what we can easily see is, or easily measure is, that we may know that if acceleration of a body can be measured, because as we have seen in kinematics, all we need to do is measure the position, the rate of change of position, that gives us the velocity, rate of change of velocity gives us the acceleration. And we may not know all the forces acting on the body. So, therefore, in such a case what we can say from the first law is that if acceleration is 0, then sum of forces, or sum of will make it external forces acting on a body have to be 0. So, let us take an example of this. Suppose I look at the sphere which is lying on ground. Then what I know is that on the sphere there is a force due to gravity, which I call it as the weight, and let me write it as m times g, and we will see more of this when we come to problems on this topic, but this is how we write. And so, this is one force which is being applied on the sphere because of the earth. Now, we also see there is a contact on the ground, and the contact on the ground we do not know what it is. Let us say we represent it by a reaction force R. Now, in this case, because we know that the acceleration of the sphere is 0, this will imply that sum of forces on the sphere must be 0, and therefore, this reaction force R must be equal to mg. So, now this is what we sometimes is also referred to as bodies in equilibrium, and when bodies are in equilibrium, then they do not move, and sum of external forces acting on a body is equal to 0. In fact, this is a branch of mechanics which we refer to as statics, where we talk of bodies which are not moving at all, and we analyze them. In fact, a whole of civil engineering structures which we talk of is based on this branch called statics, which is very important. We have seen the first law of motion. Let us see some more places where the first law is actually can be used to explain some phenomena, and let us look at some examples. Suppose we are moving in a bus, and initially the bus is at rest, and as the driver starts the bus and let us say he puts a sudden acceleration, it is observed that the body tends to fall back. And a reverse observation is felt when we are moving in again in a bus or a car, and there is a braking effect, the brakes are applied on the car and we find the body of the passenger tends to fall in front. How can we explain this? So, in both these cases, what we realize is that the feet are in touch with the floor of the bus or the car, and as the car accelerates or decelerates if it is stopping, and what we find is the feet constantly touch the floor. So, and because of friction there is no relative motion between the feet and the bus or the car. So, therefore, the feet have the same acceleration. But when we look at the human body, the human body is not one single rigid body, and the top parts of the body or top part of the body, when the bus starts, this tends to maintain its state of rest. So, while it is connected to the feet, it is not in contact with the ground. So, therefore, it tends to maintain its state of rest, whereas the feet, they move ahead. This is the case when the bus is starting to move, the feet move ahead, the body tends to maintain its state of rest, and so therefore, the body tends to fall backwards. Of course, as soon as it starts to fall backward, there is a muscular force acting in the body which brings it forward, and it comes to the same state of rest with respect to the bus. But the initial reaction is that the body tends to fall backwards, and an opposite effect takes place when a brake is applied. When a brake is applied, there is a deceleration, and the feet they feel the same deceleration. So, when the feet feel the same deceleration, they tend to stop, but the body is still in a state of motion moving forward. So, that tends to maintain its state of motion. So, therefore, it tends to fall forward when a sudden brake is applied, and then the muscular forces act on the body and bring it to a state of rest with respect to the car. Now, so what we have seen, let us try to focus on this point again. I had referred to it, that state of rest, as far as the first law goes, the state of rest and state of uniform motion. Once again, uniform motion means motion at constant speed along the same direction. This is very important, because once the direction changes, we know even if the body is moving at a same speed, there is a component of acceleration which is perpendicular to the path. This we have seen earlier. So, now when the body is in a state of rest or in the state of uniform motion, these two states are equivalent as far as effect of force is concerned. So, as far as force is concerned, whether the body is at a state of rest or it is moving, they are identical. And what we do is, so if this is same, then what we can say is such frames of reference, because state of rest or state of uniform motion will be determined with respect to a frame of reference. So, such frames of reference which are either at rest or if they move with respect to each other at constant velocities, which means uniform motion, such frames are equivalent. That means, if I say there is a frame A which is at rest, so I put a coordinate system x and y axis marked on frame A, this is at rest. There is a frame B which is moving with V which is constant. So, these two frames are frames of the type which I have described, that they are either at rest with respect to each other or moving at constant velocity, and these two frames are equivalent as far as the effect of forces is concerned. And there is a name given to this. These frames are called Galilean invariant frames. This is just a name given to this, and you may come across this, that is why we are giving this. Now, we have seen the effect of what causes a body to move. Now, what we would like to know is, we would like to quantify when a body is moving, how fast it moves, or if a particular force is applied on a body, then how much will the acceleration be. And this quantification is what will come in Newton's second law of motion. In the next class, when we discuss, we will talk of Newton's second law of motion, which will refer to the case when the external force on the body is not 0, and what effect a non-zero force causes to a body in terms of its acceleration.